But anyways, here is Harri Hätinen from Grand Crew making Supernauts game and talking about the technology behind that game. So let's give him a big hand.
All right then. Hello everyone by my behalf as well, and thanks for coming here. So during the next during the next hour, I'm gonna share some little secrets about our technology behind the game Supernauts. But at first, let me just quickly introduce ourselves. So we are Grand Crew, a game company, obviously, founded 2011, and we're based in Kallio, Helsinki, which is kind of like 2 kilometers from here, so probably not too far away. And we've already grown to 25 employees. And currently, we are now finalizing our debut game, Supernauts, as you probably know. And we are taking our time to finalize it, and not any rushing at all. We are also focused on making quality games, and our specialty is kind of been formed into creative social gameplay. So we don't want to make any nasty money-milking strategies or anything, but just want to make quality games that people play and pay for voluntarily. So that's about it. So as previously said, my name is Harri Hätinen, and I go by title Lead Graphics Programmer. And I also like to give some credit to Jarno Vuolijoki, who's behind most of the hardcore mathematics of some of the techniques I'm going to present you next. So, Supernauts. It's a multiplayer social game which we've been developing with Unity. And with Unity, we use the C# code. And it has given us pretty good hands to focus on actual stuff that actually matters. So we don't need to develop any like low-level rendering engines or anything like that. And especially because we have like only about 20 people developing the game, so we don't need to use any resources to unnecessary engine development or something like that. So a couple of words about our architecture. We have a shared code base between a client and a server side code. And the client-side code consists mostly of the Unity side consists mostly about the terrain tessellation and everything, which is going to be kind of the main topic of this presentation. So the key mechanic in our game is building worlds. So you can do lots of stuff in our game, like you can build your own home world, or you can participate in contests, or you can go and solve physics puzzles or stuff like that. But the thing that kind of combines all of those mechanics is the world building action. So everything you see here, it uses the engine, our engine, which is tessellated from the block world. And everything you see here, it's built by the players in the game with mobile devices. So that's why performance is essentially very, very important thing in our routines, because, well, if it has any glitches or if it gets annoying, people are very easily turned down by that, and then you don't get really good retention numbers from the game. So that's why it's very important. Also, in addition to the performance, we also need to have lots of visual variation, because we are modeling lots of different kinds of locations, Earth locations, cities, natural shapes, and spaceships, space turfs, and everything between. So there's kind of huge amount of variation our engine needs to work with. There's also like variations, as you can see, with the smooth and hard shapes and everything. So it's really cool. But let's get to the terrain rendering algorithm. It's first step in our engine is to just get the basic topology, the basic shape of the terrain. It's pretty much like the same kind of, if you imagine what the Minecraft looks like. And that's the first step to get in our algorithm. And also, as I should mention that an additional challenge is that updating, because we the worlds are built real time. So when players build stuff all the time, the engine needs very efficiently just update small batches in the world all the time. So that's an additional challenge that needs to be taken into account in this stage of the algorithm. So here's our example geometry. It might come from the server, and people has been built with it and everything. But the most important thing is it comes as a linear array. And the reason for that is obviously that because it's very convenient. It's probably the first data structure you learn as a programmer. And also, well, it's very convenient data structure for voxel worlds, which our worlds essentially are. And also, it allows us to create very convenient control mechanics and easy tools to build the world and stuff like that. So that's the basic data structure where our world is contained. But we'll start working that further a little bit, because obviously any GPU cannot render that directly. But the naive method to render that could be to just render cubes on each block. But that obviously is very, very inefficient and also very inflexible, well, because of a high amount of draw calls that would cause, but also because there's lots of occluded geometry that would get unnecessarily rendered, and lots of triangles that aren't visible. So what we want to track with our algorithm is to track the outer surface, because that's essentially what matters. We want to get list of vertices outside the geometry and faces around the geometry. So essentially, only thing that the player sees is this, and this is the only thing that matters. So now when we start tracking this surface area of our geometry, we started by generating a bitmap from all the geometry. That is just ones and zeros. 1 represents a block and 0 represents nothing. That's obviously very convenient, again, for our block world, because we can map just one block to one bit easily. And also, well, because it's only 1 and 0, 1 bit of data, you can pack it to very small amounts of memory. And then again, you can do also bitwise operations with this, which means that it's very fast to do parallel operations with many blocks with one operation. So very handy data structure, really. We actually use these bitmaps very extensively, from all AI problems to rendering problems. So this is kind of one example of our usage of bitmaps to generate the tessellation of our voxel world. So let's start with vertices, because that's the first thing we would like to do. So we have now generated a bitmap from all the blocks in our world. And we just reinterpret this data a little bit differently. So the 1 bit represents actually one corner of the block. It could be any block, just choose one corner from the block. And it's actually by itself almost ready representation of the corners, but as you can see, there's like some areas that aren't yet covered. So we need to, at first, just cover all the corners from our from data. So we're going to achieve that actually surprisingly simply. We just shift the data and OR it with itself to all directions. So that gives us our complete map for all the corners of the geometry. But as we saw previously, this isn't what we necessarily want. We want to get rid of all the interior corners, and we only want those ones that are on the surface to stay. And how we're going to achieve that is to take the original block map into account. And for example, let's okay, yeah, here we go. Let's for example take this one corner into account. Clearly, corner is on the surface of our geometry. And that is because it is touching at least one 0. It's touching nothing. So that's how we know that this is a corner we want to include our vertex list. On the other hand, for example, this corner here, it clearly doesn't belong in our surface vertex list because there's only blocks touching it. There's like nothingness next to it. So from this observation, we can formulate a relatively simple bit formula that is simply just we AND together all the touching blocks together and then negate it and then AND again with the corner. And this gives us this kind of end result. So it's convenient. You can encode it into like for example 32-bit integers as it is in this example here. And this is going to be very useful data for us. So we'll just kind of put it aside for a moment and start mapping the face surfaces of this data. So let's get back to the original face block data we were before. And consider this face, for example, here. Clearly, this again is a surface face, and why is it surface face? Is because it's again touching nothing. And this face, for example, it's not a surface face because, well, it's not touching nothing. So that doesn't belong in our maps. So from here we can actually, this is much easier one to deduce because, well, we just need to compare if the blocks touching the face are the same. So there's a bit operator already for that, and it's a XOR. So this will allow us to get this kind of representation of the faces. But as you can see, it's not really a complete one yet because we are still lacking all the other directions. So we actually need two more bitmaps for other axes as well. So in the end, we are going to have 3 bitmaps, one for each axis, which represents the faces of our geometry. And one side notion here is that with bitmaps generally, is that real-world scenarios, they have lots of repetition in that bitmap data. And this is something we exploit very, very much. For example, you can consider, for example, thin air, nothingness. It's only a series of zeros. That is a pattern that is going to get repeated all the time. Or just a plain ground, which is just a series of ones. That is also something that is going to get repeated very much. Or you can also consider something like a tower, because it's basically just a same kind of slices blocked on top of each other. So this is something that really, that kind of feature that is going to come over and over again. And how we can actually exploit that one is to batch our world into some convenient sized slices and then cache the data or the result from more complicated operations. This is when this allows us to make updates much more faster, because if you just do build something, small changes into your world, most of the data is going to stay the same. So that is what we are doing extensively. And we use thin slices because, yeah, people build lots of towers and all that kinds of stuff, so that's why that kind of division is convenient. But it highly depends on the scenario, what kind of thing you want to make with the block data. But back to tessellating the world. We now have the bitmaps for vertices, and then we have the bitmaps for the faces. But we still need to construct the vertex and face lists from them, because that is how the modern GPUs essentially actually render the stuff from. There's actually, at this point, there's actually quite many ways to approach this problem, because it mainly depends on what you actually want to do here. But this is just an example how we do this, is that we first iterate the face bitmaps. So we just basically find all the ones in the face bitmaps, and then when we find the face, we compute the positions for the vertices in that face, and from these positions we can look up from the vertex bitmap what the vertex index is essentially going to be. And here we can also use an optimization because we can process the vertex bitmap to be a bit histogram. The bit histogram means that in certain position how many number of ones there has been before. So we can very efficiently just map one position to the spatial position to a vertex index by this way. And generating this bit histogram is actually, there's also many ways to do that, especially if you can utilize GPU computations. But unfortunately, for example, we cannot really, in mobile platforms, we don't have very much options for the GPU computing because I think the OpenGL ES3 supports only transform feedback, so that's where we could use it. But I'm not sure if, for example, any iOS device support that yet. But there are still also other issues to take into account. I mean, this basically is enough for us to construct a very basic topology or the very basic mesh data for us. But it would be perfect as long as we would have only one smoothing group or one material or not any seams, basically. But because there's other multiple materials, there's might be many smoothing groups or something like that, we might need to do multiple vertex instances on one position. And how we do that is that how this is again a problem that you could overcome many ways. We've actually made quite naive implementation here. So we only just allocate some space between each vertex, and then we just directly compute an index for the smoothing group, and then just place it on that pivot. And when we are done with that, we just remove the gaps from the vertex list and then remap the indices from the face list. Another problem that should be addressed is the transparent surfaces. They are always kind of like the bad stuff in real-time rendering, so this is not an exception. So if you didn't take the transparent surfaces into account, then you wouldn't see any material interfaces inside the objects. Think about, for example, if you have a lake, you have a water material that is transparent and you want to see the bottom of the lake. And because we are tracking just the surfaces of these shapes, the algorithm would miss that seam between those materials. And how we overcame this one, it was actually pretty simple, was that we only just, from the very beginning, we just separate those blocks into different groups and then run this whole algorithm for them, and then we just merge these meshes again. But that's about how you create that kind of geometry. So now, basically, with this information, you could make this Minecraft type of world if you would want to. But that's not really enough for us, because we want to shape the world. We want to create all kinds of materials, lots of variation in the geometry. So we need to start shaping the vertices a little bit. And one of the kind of like the well-known de facto algorithm for this is the Catmull-Clark. But for reasons we are going to see soon, we don't use the Catmull-Clark directly, but we have made some little modifications to the basic idea of the Catmull-Clark. So to illustrate the problems with Catmull-Clark is quite obvious. So let's think this, imagine this is our original mesh we want to start modify a little bit. After one iteration of Catmull-Clark, we have already increased fourfold in our face count. And after second iteration, the amount of faces have increased already to 16 times. So that's like obviously way too much for us, and we cannot afford that really. So we have to come up with some kind of strategy to create this kind of smoothie type of look, but without doing any subdivision or without increasing the face count too much. So to explain our method, how we use it, we need, let's go through how the regular Catmull clock works. So let's consider this one corner here. This is the point P here. And then we just need to consider the nearby face points touching it. The face points are just midpoints of the faces. And then we have also edge points. And the edge points are, well, they are just like, they have this well-defined formula, and it should be quite trivial to compute if you just know it. And then we just displace the original point by this formula here. This was actually just, it doesn't have any logic behind it. I think it was originally just the factors here was just chosen so it looked aesthetic. But I think it was afterwards shown that this will equivalent produce a surface that is equivalent to B-spline. Oh, and yeah, and F and R in this formula here, they are averages of all of those points, not like anything else, so not that it would cause any confusion. So after we do this, we subdivide this cube, and we use all the intermediate points, we use those face and edge points, and then we just displace the original point by this formula. And it should produce pretty much something like this. Well, our approach to this is that at first we just pretend that we are now behind the subdivision step. So we just kind of think that, okay, we have this terrain here, or just our mesh here. We can just somehow imagine that some of these neighboring vertices here are the face points and everything. Let's just like displace this vertex by some amount. But another notion here also is that faces, they are parallelograms. And this is only, I think, approximately true after the first iteration, but before the first iteration is pretty obvious because all the faces are rectangles, and rectangles are parallelograms. And if you fiddle around a little bit with pen and paper after this, you'll notice that the average of F will have a relation with average of R. So this enables us to simplify the formula a little bit, and we want to get rid of the R because it's slightly more harder to compute and everything. So let's get rid of that. So here is again the original Catmull-Clark formula, and when we replace the R with our relation to F, we simplify a little bit. We get something like this. It's pretty simple, really. It just basically just tells us to move the point towards the face point at some certain amount. But we can also make a small notion here. Is that there's some factor here that just popped out from that formula. So let's just replace it with some custom parameter S, and suddenly we have a parameter for surface smoothness. And this is actually really cool. It's kind of like a happy accident that happened here. So we can generate lots of variation to different materials here just by tweaking the S parameter. And what's even more cool here is that the S can be negative value. It kind of produces anti-smooth shapes with that kinds of values. So it's been really useful in creating lots of variation in our geometry. However, this doesn't work without problems either. Because we are not now skipping the subdivision step, we are kind of like losing information after each iteration. So it kind of basically produces aliasing in our meshes. And how the problem arises, shows itself is that especially with cubes, for example, they tend to shrink. If you repeat that algorithm for a cube a couple of times, the vertices will approach to 0. So that is a problem. But fortunately, there's also a workaround for this. And that is because we can think what is something that we can change in the equation. And then again, there was the F, the phase point, that we could do something about it. So then we just mathematically are going to say that we want to keep the volume equal to the previous one. And you can use pretty much there's not really a right way to do that, but you can use just some nice formula you can come up with. Or you can just like make it a tweakable variable, which gives us another nice parameter to tweak our shapes with. So, yeah. So now that we have our geometry here, we just need to add some frosting to the cake. And this is not like that much technical things because we don't have any weird technical stuff here, but more like it's just design-wise a little bit unique in our game. When we started to design our rendering pipeline, or the pixel rendering pipeline, we consulted our concept graphicians a lot. So they created, programmers investigated lots of the concept graphics our graphicians had made, and then we just sat around in a table and threw some ideas around, iterated a lot, and so forth. And then we just came with some kind of plan on what we need in our pixel pipeline and what we do not need in the pixel pipeline. So then we just came up with one single pixel shader we are using in each material. It's basically quite simple shader, really, so I'm not really getting into details, but there's like a couple of unique things in our pipeline. So one thing is just that we only have one light. Because we actually spent lots of time in thinking at how we could actually render use lots of light sources with such a limited architecture. Well, it turned out that we don't actually need to do that because it turned out that we could create good enough atmosphere and good enough looking graphics without any additional light sources. So that kind of the problem solved itself by that way. One interesting concept in our pixel pipeline is also that we have a rim light almost everywhere. It's not, well, it's quite commonly known technique in theater and cinema. It's kind of, gives a nice outline to characters and gives this kind of nice glowy, spacey atmosphere and everything. But I'm not sure if many games use this kind of approach or everything, but we just found it to be very suitable for ourselves. Also, one a little bit more technical detail in our rendering, our shading, is this scary-looking formula here, which is also known by Ambient Occlusion. And this was just some tech jerking we had some extra time to do with, so it's kind of like the holy grail in the gaming industry, because I think around since mid-2000 or something like that, when someone invented the screen space ambient occlusion, almost every game started using it. And maybe almost after that, almost everyone is started to make their own versions of ambient occlusions. So it's kind of like a very usual way to show off your skills. Well, we cannot really afford post-processing, so we actually just bake the values to vertices. And to show how our technique works in principle, I just quickly go over what the ambient occlusion is in theory. So here's like our point P we want to shade with ambient occlusion. And then we have this imaginary hemisphere around it, which is kind of mathematically infinitely small sphere, but it's just here for illustration purposes. Then we have some occluding geometry around it, and which like blocks the view from the point P to the outward world. And this big object here, it occludes a little bit more, well, not only because it's larger, but also because it's facing more directly to the surface. And this one here is occludes a little bit less, but also not only because it's smaller, but also because it's facing it a little bit less. So technically, you can just make this kind of definition of ambient occlusion. It's just amount of stuff that is blocking the view outside from the point P. So from this idea, how we came through how we could shade, design our own ambient occlusion. And as I said previously, it's just computed per vertex. And how we go, we use the faces nearby as the occluders. And we are going to compute this locally only for the terrain. But because we have, from the tessellation algorithms, we have lots of information left. So we can very quickly find all the nearby faces and everything next to the vertex. So those are very convenient ones to use. And then we could theoretically, we just kind of project those points on this theoretical hemisphere, infinitely small hemisphere. And then we just project that resulting shape on the bottom of the hemisphere. And this is kind of beautiful thing here is that this projection here kind of emulates the dot product inside the ambient occlusion formula. And after this, we just simply compute the surface area or the sums of the surface areas, and that's our ambient occlusion, really. So nothing more complicated. It can get like quite complicated algebraically, but it isn't like very complicated in theory. And there's actually very many approaches you can just try to overcome this model mathematically. So you can just use your imagination, or you can try to exploit this idea somehow, or whatever you want to. But that kind of covers our basic aspects on shading. But still our world looks pretty dull, because it's missing all kinds of details and variations and everything. Everything looks like very computer generated or very computer rendered. They look like polygons. And we want to get rid of that look a little bit. We have very many methods to overcome this one, but I'm going to just quickly cover one very simple idea that when used very creatively, you can create lots and lots of variation and lots of different kinds of graphical elements into the world. And this particular method I want to go over here is edge extrusion, which basically looks like this. We have a couple of parameters such as length of the extrusion or the angle of the extrusion. And we also define that they appear only between certain seams or certain interfaces between two materials or whatnot. But what kind of effect this has in practice is something like this. For example, here we have pretty some ground, some grass and everything. It looks quite nice, but there's just pretty nasty-looking seam between the grass and the ground. So with proper configuration and proper assets, we can get it nicely, hide it nicely with very simply, and it actually looks a lot less polygon rendered right now by this way. Another application for this is, for example, roof here. Okay, it looks quite nice here, but it could look a little bit nicer if we just apply this technique again. And we can also create a little bit, if we use it a little bit more courageously, we can, for example, here's a balcony here, so just fiddle with parameters a little bit, we can get something like this. So this is something that our engine just automatically creates on that material. But yeah, okay. But that's about it of my material. Does anyone have any questions or anything? No? No one? Okay, well, thank you very much for listening. And if you have anything to ask, you can come and ask directly from me. Thank you.